In this lecture, I'm going to introduce you a bit more to the sine wave. The sine wave is one of the two key components, along with the dot product, which we'll learn about in the next lecture, underlying the Fourier transform. And the Fourier transform, in turn, is perhaps the most important algorithm or tool in time-frequency-based analyses. So a sine wave, as I'm sure you already know, is a cyclic process. It's something that has a rhythmic component. It keeps going up and down over time. It looks something like this. We learned already that the equation for a sine wave looks something like this. It's a sine 2 pi ft plus theta. A is the amplitude or the height of the sine wave. F is the frequency. T is for time, and when time is given in units of seconds, then F, the frequency, can be given in or interpreted in units of hertz. And theta refers to the offset or the position of the sine wave at time equals 0. We can translate this equation into MATLAB code as something like this, and we'll see this in MATLAB in a few minutes. So here we have a sine 2 pi ft plus theta. Now you might be wondering, why does this sine wave go up and down like this? What causes it to go up and then stop and turn around and go back down again and so on? We will learn in a future video that, in fact, what you see here as going up and down is really just a projection onto two dimensions, a time dimension and a real dimension. In fact, these sine waves are better characterized as three-dimensional processes. You can kind of imagine a slinky going over or going through time. So we have the time dimension, the real dimension, and this is something called the imaginary dimension. So this is the imaginary part of the sine wave. This produces something called a complex sine wave, complex meaning it has a real part and an imaginary part. I'm going to discuss in more detail what this means and why we need this imaginary part to extract time frequency information in the future, in a future lecture. But for now, you can just imagine that moving this slinky around so that we ignore the imaginary axis and we look at only the real part and the time dimension, then we would get something that appears to go up and down like this. Again, this is just something to whet your appetite for a future video where we will discuss this in more detail. There are three characteristics that fully explain all of the sine waves in our universe. Maybe in other universes there are 2 or 5 features that characterize oscillations, but in our universe you can characterize all of the sine waves in existence with only 3 features. And the first feature refers to the speed of the oscillation, and we can quantify this as the time it takes to get from one peak to the next peak, or one trough to the next trough. For EEG analyses, we often use the unit of hertz, which is 1 over seconds. And so 4 hertz means 4 cycles per second. So if this sine wave were at 4 hertz, we would say that 1, 2, 3, 4. So this would be a 1 second period of time. This feature is called frequency. It answers the question, how fast is the oscillation going? So here, this is an oscillation of around 6 hertz. And this is a faster oscillation of around 25 hertz. Okay, so that's frequency. That's one of the features. The next feature refers to the position along the sine wave, which we can speak about semantically as peak or trough or downslope and upslope. But in order to be a little bit more precise, we use measurements in terms of radians that refer to each of these points. So this is called phase. Finally, we want to know, or we can characterize the ongoing amplitude of the oscillations. And here, this is not so much referring to the height at any given time point. This is more related to the phase, but here we're referring to this so-called analytic envelope that's going on top of this oscillatory process. So you can imagine, or I imagine, laying a blanket on top of this sine wave. So it wouldn't go down into these dips. The blanket would be kind of just highlighting these overall features. So here you can see it's going down and it's going up. This feature is called power. It's also sometimes called amplitude. Power is just amplitude squared. And so in many instances, the two terms can be used interchangeably to indicate the same meaning. So again, here you see higher power and then lower power. Okay. Now, one of the important ideas, or perhaps the driving idea underlying the Fourier transform, is that we can represent complicated signals by summing together, by mixing together several sine waves of different frequencies, different phases, and different amplitudes. And so here I have an example of this. These are simulated data. Obviously, these are not EEG data, hence the apology quotes here. You can tell these are not real EEG data because they're a bit too simple and predictable, or stationary, we might say. And it's lacking high frequency features, and obviously it's lacking noise. So this is not real EEG data. And I'm sure you can see where this is going. This signal I simulated just by summing together 5 different sine waves. So I took 5 sine waves, each one with its own frequency, its own power, and its own phase. And I summed them up at each time point, and that gave us this more complicated and more interesting looking signal. So now we can switch to MATLAB and run some of this ourselves. Okay, so here I define a variable for frequencies. I'm specifying it to be 2 Hertz. I know that this is in Hertz because I'm specifying the time vector to be in seconds. And this is in seconds also, so I don't have a separate variable for this, but I'm defining this with a sampling rate of kilohertz, so 1 sample every millisecond. Here's our familiar looking sine wave. So we have we're not defining an amplitude here, so it's implicitly set to 1. Of course, I could just leave it like this. A sine 2 pi ft plus theta, and here again the theta is, I'm setting it to 0, so we also could have just deleted it. So we can run this line of code and get a very nice looking perfect sine wave. Now what we want to do is create several sine waves and sum them together to get a slightly more interesting looking signal. So here I do define a sampling rate. Here I have a vector for frequencies, a vector for amplitudes, and a vector for phases. There are 5 elements in each vector because I'm going to create 5 sine waves. And so you can add more to this if you want, but just make sure that if you add another frequency, you also have to add another amplitude and another phase value. Okay, and so here in this loop, we are creating sine waves, and you can see this looks very similar to the code you've seen before. The main difference is that this frequency, the amplitude, and the phase is going to vary over, or it's going to be different at each loop in this, or each iteration inside this loop. And that's going to allow us to generate a matrix of individual sine waves. Here on line 43, I initialize this matrix with zeros. Initializing matrices is always a good idea. First of all, it forces you to think about what the sizes of the matrices are, which is generally a good idea. Second of all, initializing will help speed the MATLAB computation time, so your code will run a bit faster. And third of all, it will help you prevent making errors. Okay, and now what we're going to do is basically do some plotting to recreate these diagrams here. Okay, so we can try running this. Oops, and we get an error. We get an error because line 59 is incomplete. I just wrote the plot command here. What we want to do is, inside this loop, plot in an individual subplot, plot only one sine wave. So it's going to look like this. So here we have one sine wave and then so on for all the sine waves. Okay, so if you'd like to have a little bit of a challenge, you can pause the video now and try to finish this line yourself. So we can set the x variable to time, and now we want to plot sine wave, and let's do line width 2 to make the line a little bit thicker. And okay, so this part looks fine. This part doesn't exactly look like what I had in the PowerPoint side, because you can see all the sine waves are being plotted in each of the subplots, which is looks kind of neat, but it's not really what we want. The problem here is that I am plotting the entire sine waves matrix at once, and so what we want is to plot only one of these sine waves per iteration inside this loop. And here we go. This very nicely replicates what I had in the PowerPoint slide. Okay, here we see two different but equally meaningful representations of the same sine wave. This slide I already went through a few videos ago. I think it was the introduction to or the broad overview of data analyses in cognitive electrophysiology. So I'll just go through it very briefly here. This is called the time domain. This is called the frequency domain. In a few lectures, you will learn how to make these kinds of plots sort of by hand, how exactly to go from the time domain to the frequency domain, and how to go from the frequency domain back to the time domain. For now, just focus on interpreting the frequency domain, because it's a little weird at first to understand how these two figures show the same information. So here, this sine wave, this is a 1 second tick mark. So here we see that this sine wave has 1, 2, 3 cycles within a 1 second period. And so now here in this plot, we see a frequency of 3 hertz, 3 cycles per second, and we have an amplitude of 1. Now this may seem a bit weird to you, because you might be thinking, hey, we go from -1 to +1, so shouldn't the amplitude be 2? In fact, we measure amplitude as half the distance of the peak to trough. Or you can measure it as going from 0 to the positive number. I promise I will explain exactly why this is the case in a future lecture. But for now, just sort of keep it in mind that the amplitude here is measured not as the trough to peak distance, but half of the trough to peak distance, or more precisely, the 0 to peak distance. Okay, so here's one sine wave. Here's another sine wave. You can see it is a faster frequency and it has a smaller amplitude, and so that's also reflected here. And now when we sum these two sine waves together, in the time domain we have something that looks like this, and in the frequency domain it's very clear that this signal comprises these two components, one component at 3 hertz and one component at 8 hertz. Now the more sine waves we add together, the more complicated the time domain representation becomes, the easier and more straightforward it becomes to visualize and quantify and understand the components in the frequency domain. So this you can see here. Here, compare this time domain representation. This is obviously a sum of several sine waves, but it's difficult to tell exactly how many sine waves there are and really what the frequencies are, except maybe for 1 or 2 of the sine waves. But here in this frequency domain plot, it is really exceedingly clear that there are 4 sine waves, and their amplitudes are 2, 10, and whatever these guys are. Okay, even more the case here, where we have the same signal but just some noise added. You can see some broadband noise, and it's very difficult looking in the time domain to understand what the constituent parts are of this signal. Okay, so let's take a look at this in MATLAB. So now, if you go down to the cell that starts on line 63, some of this code may look confusing if you are a bit new to MATLAB or new to data analyses in MATLAB, because I'm not yet defining what this function is, the FFT function, or why we have to divide by the number of time points, or how exactly we create this vector of frequencies and hertz and why it goes to half the sampling rate. I promise that these things will become clear in the future. For now, I just wanted to focus on just transforming this, the idea that we can transform this time domain signal into the frequency domain signal in a fairly straightforward manner. And so now we can go back and compare each of these, so we can see, for example, 10 hertz looks like there's an amplitude of 15, and here we go back, and indeed we specified that the 10 hertz component in the data has an amplitude of 15. So that's very nice. That just reconstructs the time, or gives us the information from the time domain signal in a way that is easier to understand and easier to quantify compared to this version in the time domain. So, as I mentioned in the beginning, sine waves are incredibly important in signal processing, and in particular in time-frequency-based data analyses. Once you have a grasp of sine waves and the dot product, which is the focus of the next lecture, it will then be very straightforward and very easy to understand how the Fourier transform works. So much so that, in fact, you will see in 2 lectures we will write the Fourier transform out by hand in MATLAB and show that it produces exactly the same results as the FFT function.